Okay, so this is section 9.4. We're going to be talking a little bit about vectors. Now, we've actually been drawing vectors this whole chapter. We just haven't been referring to them in that specific word. So here's the definition up here. Okay, vectors have both magnitude, so it's the length of the vector, and the direction. So you can see where this might play into physics with airplanes and boats, right? A northeast, southwest, a bearings kind of thing. One thing that's kind of confusing is there are several different notations. The first notation that we're going to talk about is called component form, where there's an A and an I, a B and a J. And this can be a bit confusing because remember with imaginary numbers, the I was on the second part. This I is actually a different I, and we'll talk about that more in class. So one thing we might talk about is the position vector P with the initial point Q as a terminal point. So if I ask you to find me a position vector, let me just make one up here. So if I gave you P as 1, 7, and Q as 3, 5, and I asked you to find me the position vector of it, if we follow this formula here, I know it looks a little funny, but there's kind of these squared off slanted brackets, and it's kind of like the slope formula, where you're taking the x of the second one minus the x of the first one, and then the y of the second one minus the y of the first one. So the position vector for that example I just made up quickly would be 2, negative 2. And we'll talk about how to plot those. Very similar to what we've already been doing. Okay, this next little part is just kind of using some pictures of different vectors and show how we can add them, subtract them, multiply them by different numbers, and just kind of see what's happening here. And I want you to try to think every time we do something like this, even though it's going to be a rough sketch, there are some application questions we'll talk about later. For example, if I have this vector V here, right, and then a vector W here, something we could talk about is this. You have a plane flying along this vector, and you have a crosswind going in this direction. So I'm just kind of imitating V and W here, right? And then what happens when you add these two together? Well, the airplane, if you think about it, and it's a little more complicated than this, but the airplane would then fly more along this vector. And so I would call that one a V plus W. Okay? So if you're adding two together, you're kind of taking both vectors, putting them together, and then connecting the starting of the first vector to the end of the second vector. Okay? All right, now, if we look at this next example, very similar, except V minus W. So think about this. You have V going along, like it was in that first example. This is kind of a rough estimate, right? It's kind of that direction. And then you think about W, normally would be going like this, right? I'm going to do kind of a dotted line. Now, just like things we've talked about before, a negative W is going to go the opposite direction. Okay, so this one here would be W. This one's going to be a negative W, and here's our V. So if you talk about what we say the resultant vector, when you do these two together, you're going to take the beginning of the first vector and connect it to the end of the second one. Okay, now, we can also take a vector, and we can multiply its length by any constant we want. So if you look at number 3, think about this. V's going this way, right? 2 V's would be something like that. And then if W's pushing down this way, and I do 3 little W's, it could be something like that. So once again, really rough sketches. Now if I take the beginning of the first one, connect it to the end of the second, there's my 2V plus 3W. Okay? All right, this next one over here, if I take 3 vectors and I do all 3 together, same concept, so let's just do it slowly here. Okay, here's my 2 V's. All right, so V1, there's another V. I have a negative W, so remember that means I backtrack this way, negative W, and then to the tip of that negative W, I'm going to do a U, so something like that. Okay, then remember, the resultant vector, the final vector, is going to be from the beginning of the first one, and this might not be the prettiest picture, but from the beginning of the first one to the end of the second one. And that was supposed to be a straight line, but something like that. Now the next thing, the position vector. We talked about this just briefly up in the definition, so let's just do one more. So when you see this when you see the PQ, and it has this little ray above it like from geometry, that means the vector, the position vector from P to Q, where P is the first point, Q is the second point. And just so you get used to different types of notation, instead of a P and Q, we're using a P1, P2, but it's the same idea. So if I'm doing the PQ and I follow what the formula says, I'm going to do the x-coordinate of the second point minus the x-coordinate of the first, that changes to a +1, just like slope, and then the y of the second one minus the y of the first. So the position vector in this new notation would be 5, 4. Okay, and then once again, just to get used to the different notations you're going to see throughout this section, there's also that component form I talked about briefly. So component form is with the i's and the j's. So 5i, and that's, remember, it's not imaginary I, it's a different kind of I, and 4j. Okay. The magnitude of a vector comes from Pythagorean theorem. So these kind of double bars, I know it's a little blurry on my copy here, the double bars with the vector letter in it, that stands for the magnitude. How long is the vector? Okay? Now, it kind of makes sense, right? That it's the square root of a squared plus b squared. So if I'm doing the magnitude of any vector, I draw my triangle and I can do the lengths. Now, little note here, even though it's going to sound weird, vectors with the same magnitude and direction are considered equal vectors even if they have different starting points. Okay, so consider something like this. If I have a vector going, I'm just going to try to draw it as a perfect 45. And let's say it's 5 units long. Okay, then I draw another vector and I start way down here, but it's going the same direction and it's also 5 units long. I would consider those equal vectors even if they have different starting points. We'll talk, like I said, much more about that. Alright, the next part is going to seem pretty straightforward, but I do want to show you a couple examples so you don't get confused when you see it. Alright, we can add and subtract vectors algebraically as well as graphically. So we did those rough sketches where we did a v plus w. We can also add them when they're in component form like this with the 2i and the 3j. So when you do that, it's kind of like from Algebra 1 where you're combining like terms. So the i's, v plus w, would be 5i. And then the j's, I combine those, you get negative j. Right? Nothing too crazy. Let's do one more. Let's actually skip over to part C. So, just like from Algebra 1, 2v would be 4i plus 6j. I'm just doubling both of those. And then a minus 3w. Let me go ahead and do the minus. I'm going to write it out, just so you don't get thrown off by that negative. Here's my minus 3w part. Okay. And then you can see, I'll show a little bit of work. You probably don't even need to show this much. Distribute that negative 3 through. And then finally combine like terms. Okay. The last example over here, part D, means the magnitude of v plus the magnitude of w. Now, remember to find the magnitude of v. It's from Pythagorean theorem. So it would be 2 squared plus 3 squared. That's magnitude v. Plus magnitude w will be 3 squared plus 4 squared. Okay, so what I have here is a root 13, and root 25 is just 5, so I'm going to leave it like that. Now, the unit vector, what that means is the vector has magnitude 1 in the direction of some given vector v. Okay, now, there's a cute little way to find it, right? If you can memorize that, it's really not so bad. It would be the vector itself over its magnitude. That's going to give you a unit vector of magnitude 1 in the same direction. So what I'm going to do in this video is show just using this little shortcut, and then on class I'll show you another way to find it if you want to know where that formula comes from. So here we go. The unit vector would be v is 4i minus 3j. Okay, there's the given vector. The magnitude would be, let's work it out even though you might be able to see it already, 4 squared plus 3 squared. So it would be 4i's plus 3j's all over 5. And then when you're writing these in a plus bi form, make sure you take the 5 and divide it into both numbers. So these two values should be separate, the i's and the j's. So if I go like this.
What are you trying to do?
Now we're also going to have a couple questions where they might not tell us a whole lot about the vector. They'll just give us some different pieces of information. For example, this next one says, find a vector v whose magnitude is 3, so that means I already know what the magnitude is, and whose component in the I direction is 3 times the component in the j direction. Okay, so I don't really know. I know that the magnitude of v is 3. It's a good starting spot. And all I know is the part in the I direction is 3 times as big as the j direction. Now, when this happens, okay, so if I set up my magnitude, right, 3 equals, sorry about that, equals, it would be something squared plus something squared. I don't know what those are. But I do know that the part by the i's is 3 times the part by the j's. That's what that means. So, if you look at a little bit of algebra here, okay, so I would go 3 equals, this would then give me 9x squared plus x squared. And again, this is still under the root. Sorry about that. Okay. I'm going to go ahead and square both sides here, so I get 9 on this side now, and I have 10x squared left here. So what I get is x squared equals 9 over 10. Okay, and x would then be, it's going to look funny, but root 9/10, which is 3 over root 10, which is 3 root 10 over 10. So if x is 3 root 10 over 10, then I know 3x is 9 root 10 over 10. And remember, the 3x part goes with the i's. So I would write my final answer like this. 9 root 10 over 10 I plus 3 root 10 over 10 j. Okay, this very last example is so similar to what we're doing. I hope it all makes sense after we do this one. It says find the vector in component form, so I need i's and j's when I'm done, with magnitude 3 and angle 240 degrees. So now we're talking about an angle here. Okay, so we know 240 should be right here, okay, with a 60-degree reference angle, which means this is going to be my negative root 3, negative 1, 2. I got it all labeled up. And I want to know the i's and j's that go with it. Okay, so you can do a couple things here. You can transform this triangle here into what we have and change the radius to 3. That would be a nice way to do it. You can also go into some of this that we know. X equals r cosine theta and y equals r sine theta. Either way really will work. I want to show you kind of the geometry approach rather than the trig approach and just see how that sits with you, and I can do the other approach in class as well. Okay, so let's try it this way. The angle we're not changing. It's still going to be here in the third quadrant. It's still going to be a 60-degree reference. Now, if I change this to magnitude 3, it means the hypotenuse is 3. And in a 30, 60, 90, the one across from the 30 is half the hypotenuse. So what if I call it 3/2? And the one across from the 60 is root 3 times what we just found. So 3/2 root 3 would look something like that. So if I write it in component form, it would be negative 3/2 I, so the I is in the x direction, minus 3 root 3 over 2j. So that would be kind of a geometry approach. And I can show, this trig approach as well, because that should make sense too. Okay, tomorrow in class we'll go over all this, and we'll also touch on some of the types of application and word problems where all of this is used.